All right, for change of pace, rational functions and their graphs, section 3.5. All right, so we've actually already talked about the first part of this, the domain. All right, so the domain of a rational function, okay, is going to be all real numbers from negative infinity to infinity, except for whatever makes the bottom 0, or the denominator 0. So if you're looking for the domain, you don't have to worry about the top as far as the domain's concerned. We'll deal with that in a little bit. All right, but if you set the bottom, set the denominator equal to 0, and solve that out, then you get what is not in the domain. All right, so the domain for this function is going to be from negative infinity to our problem point at 3, with the parentheses, union with a parentheses, our problem point to positive infinity. All right, and so what that tells us is that all of the numbers except for 3, I can plug into this function and I can get a number value. Okay, but if you plug 3 in, you get 3 minus 3 on bottom, which is 0, and you can't divide by 0. Okay, even though the top would also give you 0 if you plug 3 in, there's a problem there. There's not anything existing at that point. All right, so if you look at the second one there, you set the bottom equal to 0. All right, you can either factor this into x plus 3, x minus 3 is equal to 0, or you could bring the 9 over and say x squared is equal to 9. All right, either way though, if you work it out correctly, with the factored form, you could subtract the 3 on the first and add the 3 on the second. If you brought the 9 over, you would take the square root of it. All right, but either way, you get the x is equal to either positive or negative 3. So the domain for that one is going to be from negative infinity to our first problem point at negative 3, union with that same problem point, negative 3, to the next problem point of 3, then union with that problem point all the way to infinity. Okay, so you go from negative infinity, you end at positive infinity, and then wherever your problem point is, you stop there, put that number down, start there, go to the next one, start there, go to the next one if there happen to be more of them, and then where the last problem point is, go to infinity. All right, then you can look at C here. If we did the same thing, if we set x squared plus 9 equal to 0, all right, this one does not factor. If you brought the 9 over by subtracting it, then when you take the square root, all right, you're taking the square root of negative, which gives me imaginary numbers. Okay, an imaginary positive or negative 3i. All right, and since these are imaginary, then you have your domain goes from negative infinity to positive infinity because there are no problems. All right, and that's the domain. Now, along with that, we have something called the vertical asymptotes. Okay, and we'll see that in graphically in a little bit. All right, but what an asymptote is, it's a number, okay, or it's a vertical line. A vertical asymptote is x is equal to some number, whereas the graph gets really close to it from either side. It never actually gets to that point, never gets to that value of a. All right, and the y values get either higher and higher and higher and higher going towards infinity, like you have on the first two from the left and right, or they go down forever and ever towards negative infinity. Okay, and so an asymptote is a line the graph is not going to cross, okay, at least vertical asymptotes. All right, how you locate vertical asymptotes is you make sure that there's nothing in common on top and bottom when you factor it, and then whatever makes the denominator 0, the bottom again, equal to 0, then that's going to be a vertical asymptote. So it's almost the same thing as the domain, except for we have to make sure that this is in simplest form. Okay? We have to have simplest form for a rational function. Okay, if something crosses out, then that's no longer a vertical asymptote. All right, so if we look at these examples here, all right, the top is x, so that doesn't factor. The bottom factors into x plus 3, x minus 3. But since nothing cancels out on top and bottom, we don't have an x plus 3 on top or x minus 3 on top. And we don't have just a single x by itself because the x's are inside these factors. Nothing cancels out. So if you set both of those equal to 0, your vertical asymptotes, which I'm going to abbreviate as VA, vertical asymptotes for VA, is going to be x is equal to negative 3 and x is equal to positive 3. All right, on G, we have x plus 3 on top. Since we have a difference of 2 squares on bottom, that again factors into x plus 3, x minus 3. All right, but since the x plus 3 on top and the x plus 3 on bottom are common, those cancel out. And so you're left with 1 over x minus 3. And now you look and see what makes the denominator 0. In this case, it's just the 3 when you solve that out. So x is equal to 3 is our only vertical asymptote for that function. All right, and then if you look at C, all right, the top is good. The bottom won't factor. All right, so if you set the bottom equal to 0, x squared plus 9 equals 0. You have that same problem we had in example 1. If you subtract the 9 over, you get a negative 9. And then when you take the square root, it's imaginary numbers. So on this one, there's going to be no vertical asymptotes. All right, so if you want to pause it now, and I'm going to write the answers up here for the checkpoint. All right, I'm writing them now. X equals 1, x equals negative 1. For B, you would have x is equal to negative 1, and then no vertical asymptotes for C. All right, those are vertical asymptotes. Now, rational functions also have what we call horizontal asymptotes, which are, again, imaginary lines or numbers. Okay, this is going to be a horizontal line. Y is equal to a number. All right, that as you go towards the end of the graph, either toward positive infinity or technically negative infinity, so either to the left or to the right, the graph approaches that number, it approaches that line, it gets really close to that line, but it never actually hits it. Okay, it could be coming from the bottom, it could be coming from the top, doesn't matter. Now, the difference between horizontal and vertical asymptotes, besides one's horizontal and one's vertical, is in a horizontal asymptote, you can actually cross the horizontal asymptote, but you cross it somewhere in the middle, and towards the end, you're still having that same limiting behavior. All right, and so how to locate horizontal asymptote? It's all about the highest exponent. It's all about the degree. Okay, so you're going to look for the highest exponent on top and the highest exponent on bottom. Okay, everything else doesn't matter as far as horizontal asymptote. So highest exponent on top, highest exponent on bottom. All right, and then you're going to have one of these three things. Okay, if the highest exponent is on bottom, okay, so if the denominator is bigger, so if the bottom is bigger, then you're going to have y equals 0, which is your x-axis. That's going to be your horizontal asymptote. All right, skip on down to 3. If the top is higher, the top is bigger, you're not going to have a horizontal asymptote. Wow, I can't spell bigger today. There we go. The top is bigger. You're going to have no horizontal asymptote. All right, and the only other case is if they're the same, then you take the coefficients of those highest exponents and you make a fraction out of them. So if they're the same, you have y is equal to the leading coefficient of the top divided by the leading coefficient of the bottom, and that is your horizontal asymptote. All right, so if we look at these, A, find the horizontal asymptotes. All right, so again, we're looking at highest degree. The exponent on top is 1. The highest exponent on bottom is 2. So since the bottom is bigger than the top, we have y is equal to 0. Bottom is bigger than top. So the bottom is bigger or higher. All right, on B, you have an exponent of 2 on top and an exponent of 2 on bottom. So since they are the same, we're going to say y is equal to the leading coefficient of the top, so 4, divided by the leading coefficient of the bottom, which is 2. So you end up having a horizontal asymptote of y is equal to 2. All right, and then on C, you have a 3 on top and a 2 on bottom. So that means the top is higher. Since the top is higher, we have no horizontal asymptote. All right, so go ahead and pause it real quick. Try the checkpoint. All right, hopefully you figured those out and paused it and come back. So on this one, you have y is equal to 3 because the top and bottom are the same, and 9 divided by 3 is 3. For B, we have y is equal to 0 since the denominator and bottom is bigger. And on C, we have no horizontal asymptote. All right, so graphing these things now. All right, this first one example is going to be a little bit different from what we've talked about. Okay, but there's two main common rational functions, 1 over x and 1 over x squared. And 1 over x, you'll have on the left side, you'll have it in the bottom third quadrant. Okay, so it's going to be coming, have a horizontal asymptote of 0, y equals 0. So as I go off to the left, it's getting closer and closer to that horizontal line. And then it comes through, and then it goes down forever and ever because we have a vertical asymptote of x equals 0. And then on the right-hand side, it's going to come from the top, and then it's going to flatten out towards the x-axis. On the y equals x squared, both of our little arms of our function here are going to be on top. Okay, flattening out, then getting really, really steep, and coming from the top, really, really steep, and flattening out. All right, and so this first example, we use the fact that we know what f of x equals 1 over x squares look like, and we can do transformations like we did in the previous chapter. All right, so since we know that 1 over x squared looks like this, that's what y equals 1 over x squared. All right, then when we look at our g function here, all right, we look inside the parentheses. That tells us horizontal movement, horizontal transformations. So the minus 2 would tell us I'm going to move it to the right 2. All right, remember inside means I'm going to move it left or right, opposite what you think. So minus actually means move to the right. All right, and then the plus 1 up top tells me I'm going to move it to the up. Move it up. The number on the outside moves it up or down just the way you think it should go. All right, so how does that work when we graph it? All right, well, normally on the 1 over x squared, we have horizontal and vertical asymptotes on the axes. We're going to shift those. All right, so our vertical asymptote, which was on the y-axis, is going to be moved over too. So we're going to draw us a vertical line, a dotted line there, 2 to the right of the y-axis. All right, and then we're going to do our up movement. Okay, normally our 1 over x squared is on the x-axis, so we're just going to move it up 1, so where it's up at 1. All right, so we have those axes. And then from there, we're just going to draw out this shape, but based on those dotted lines. Okay, and we can plug some numbers in to figure out exactly where stuff goes, but I'm not really concerned with that. Okay, we're just concerned at this point, what does it look like? So it's going to look like this. And then come over here, come from the top, and it's going to look like that. Okay, and it actually be more symmetrical than what I drew it. Okay, but it looks almost exactly like the 1 over x squared function. The only difference is it's been shifted right and up slightly. Okay, so you can pause it and see if you can figure this one out. All right, here's the answer. 1 over x normally looks like this. All right, so the plus 2 on the bottom means I'm actually going to go to the left 2. All right, because plus means left or right, or plus means left. Okay, so whatever's on the bottom is left or right, and the number out to the side tells you up or down. In this case, down 1. All right, so when I draw my asymptotes, I'll have left 2, so 2 to the left of the y-axis, and then down 1. All right, and then from there, we're just going to draw the same shape, but using these dotted lines as our boundaries. Okay, so to the left, we're going to be on the bottom. So we're coming around and look like this. And then to the right, we're going to be up top. All right, hopefully you got that one. Now, when they're not just the normal, common rational functions, here's our strategy. Okay, if we want to, we can figure out symmetry. I'm probably not going to do that. Okay, you can find the y-intercept, okay, by plugging in 0. So y-intercept, plug in 0. Find the x-intercept by setting the top equal to 0. All right, vertical asymptotes will set the bottom equal to 0. Okay, and again, we've got to make sure that is, in fact, in simplest form. All right, for horizontal asymptote, we look at our degrees, so our exponents on top and bottom, using that rule. And then it says plot at least one point between and beyond each x-intercept and vertical asymptote. Okay, and we'll see how that goes here in a second. All right, so let's look at this one. All right, the first thing they told us to do was, after symmetry, is find the y-intercept. So to find the y-intercept, you plug 0 in. So get f of 0 is equal to 2 times 0 minus 1 over 0 minus 1. So it gives me negative 1 over negative 1, which is a positive 1. So I know it crosses the x-axis, or excuse me, y-axis, right up here at 1. All right, second thing we're going to find is the x-intercept. To find the x-intercept, we're going to set the top equal to 0. So we're going to say 0 is equal to the numerator of 2x minus 1. All right, we add the 1 over. Gives me 1 is equal to 2x. We divide the 2. So x is equal to 1/2. We know it's going to cross the x-axis right here at 1/2. All right, then we find our vertical asymptotes. Vertical asymptotes. Our vertical asymptote, we set the denominator bottom equal to 0. So 0 is equal to x minus 1. Okay, we add the 1 over. 1 is equal to x. And so we know we have a vertical asymptote at 1. So right here, we've got a vertical asymptote. All right, for horizontal asymptote, we look at the degrees. Say, hey, well, the highest exponent on top is 1, the highest exponent on bottom is 1, so we take their coefficients. We say y is equal to the 2 on top and the 1 understood 1 on bottom, and so we get y is equal to 2 is our horizontal asymptote. So we come up here to 2 and draw a vertical line, horizontal line across. All right, and then we're almost done. Okay, we just have to graph. Okay, now, what I like to think on rational functions, we have the parts of our graph are split up by the vertical asymptote. So on here we have one vertical asymptote, so we need to know what happens to the left of that and what happens to the right of that. Okay, because of the x-intercept and y-intercept, we know what happens to the left. It's going to be below the dotted line. Okay, and the graph on these is either going to be a below or above if you just have the one vertical asymptote. So on the left-hand side, I know my function is going to look like this. It's going to hug that horizontal asymptote. It's going to go through those 2 points, kind of curving through those, and then it's going to get closer and closer and closer and closer and closer to that dotted line. All right, so we know what that side looks like. So now we got to figure out what happens on the right side. So on the right side, what we do is we just plug a number in. Okay, what is a number that's to the right of our vertical asymptote there? Our vertical asymptote is at 1, so if we plug in, say, 2, we figure out where that would be. So if I plug 2 in, that will give me 2 times 2 minus 1 over 2 minus 1. So 4 minus 1 is 3 over 1, so 3. So now I got the point 2, 3. All right, and that's actually enough. Okay, because on the right, I wanted to figure out, is it on the top or is it on the bottom of the horizontal? And since that 2, 3 is on top, I know the rest of it has to be on top. Okay, asymptotes act like boundary lines. All right, so I come towards it. It's going to hug that vertical line, and then after I pass through the point, it's going to hug the horizontal line. So it looks a lot like our 1 over x. All right, this one will work exactly the same way. So try this one out, and I'll put the answers on the worked PDF on modules. All right, so let's take a look at this one, example 6. All right, so y-intercept, we plug 0 in, so f of 0 is equal to 3 times 0 squared over 0 squared minus 4. So that gives me 0 over negative 4, which is 0. So now it crosses right here at 0. For x-intercept, we set the top equal to 0. All right, if you divide the 3 out, you get 0 is equal to x squared, And so you end up getting that same 0. That's the only place where it crosses. All right. For your vertical asymptote, you set the bottom equal to 0. All right, since it's a difference of two squares, it factors into x plus 2, x minus 2. And when you set those, you actually have 2. Set those equal to 0. You actually have x is equal to negative 2 and x equals to positive 2. You have 2 vertical asymptotes. All right, so when I draw those out, there we go. The pin's back working now for a second at least. All right, and now I've got a vertical asymptote at negative 2 and a vertical asymptote at positive 2. All right, and then I got to find my horizontal asymptote. Okay, there could be multiple vertical asymptotes, but for rational functions, you only have one horizontal, if you have one at all. All right, so you look at the exponents. Top and bottom are both 2. So look at the leading coefficients, 3 and 1. And so my horizontal is y is equal to 3. So I draw that line out. 3. All right, and so now I've broken my graph up into left, middle, and right. All right, so I need to figure out what happens to the left, what happens in the middle, and what happens on the right-hand side. All right, so let's plug in something to the left. Do a little thing for my points. Something that's to the left of negative 2 is a negative 3. So f of negative 3 would be 3 times negative 3 squared over negative 3 squared minus 4. So the top will give me 27. And the bottom will give me 9 minus 4, which is 5. Yeah, fraction. So 27 divided by 5, okay, is a little bit more than 5. It's like 5 2/5. So I know that that point is going to be up here. So when I draw the graph on the left-hand side, I know it's going to be on the top section. All right, let me figure out what happens to the right. So something that's to the right of 2 would be like 3. So if I plug 3 in, I'm going to get exactly the same thing I got with the negative 3 because of the squaring. All right, I'm going to get that same 27 over 5. So I'll also know at 3, I'm up here at 5 2/5. And so to the right, I also know I'm up at the top part. So the graph is going to come through and look like this. All right, so now I got to figure out the middle. I'm actually going to do 1 point on each side of that x-intercept. So I'm going to figure out what f of negative 1 is, and I'm going to come back and I'm going to find what is f of 1. So if I plug the negative 1 in, all right, I get 3 times the negative 1 squared over negative 1 squared minus 4. That will give me 3 on top. 1 minus 4 is a negative 3 on bottom. And so it gives me a negative 1. So I know I'm right here. All right, because of the symmetry of this thing, when I plug the 1 in, I'm going to get exactly the same thing. I'm going to get that 3 on top, and then 1 minus 4, negative 3 on bottom, which gives me negative 1. So I've got that point there. All right, so you can kind of tell what's going on. It looks like kind of like a parabola shape from the x-axis, I'm going to come to the left and go down and get closer and closer and closer and closer to that dotted line. Looks like mine crosses it, but it doesn't actually on the real life. All right, and that's what your graph looks like. So once you have your vertical asymptotes, figure out what happens to the left, right, and in the middle when you have multiple vertical asymptotes. All right, this one will work the same way. You'll see it on the worked out notes. All right, and then finally have this one. Okay, and this one's going to look really just totally different than all the other ones. All right, for our y-intercept, we plug 0 in. So that would be 0 on top. 0 to the fourth is 0. 0 squared is 0 plus 1. And so we got 0. So it crosses at the x-axis. Okay, crosses at 0. All right, our x-intercept is going to be exactly the same thing because of that plugging in 0. Set 0 equal to x to the fourth. When you take the fourth root of both sides, you get x is equal to 0. All right, for vertical asymptotes, you set the bottom equal to 0. All right, but when you subtract the 1 over there, take the square root, you get imaginary, so you have no vertical asymptote. All right, and then for horizontal asymptote, we look at the degrees, and since the degree on top is bigger than the degree on bottom, we have no horizontal asymptote. All right, so now we just got to figure out what's going on either side here. So let's look, we got to plug in some points. So something that's to the left of -1 and something that's to the right of, excuse me, to the left of 0 to the right of 0. So I'm actually going to try a -2. If I plug a -2 in, I get -2 to the fourth over -2 squared plus 1. All right, the top gives me 16. The bottom gives me 4 plus 1, which is 5. And 16 over 5 is 3 1/5. So I know I'm going to be up here at just past 3 when I'm at -2. Okay, and then let's plug something to the right. So let me plug 2 in. It's going to end up giving me exactly the same thing because of those exponents. It's going to give me 16 over 5. All right, which again is 3 1/5. So it'll be up here. So this one actually looks like a parabola when I graph it out. It would actually go through those points. But you get the idea. All right, so just because something's rational, most of the time it looks like this with all the asymptotes going on. But sometimes you could get one that looks just like another polynomial function. All right, try those on MyMathLab. Email me with any questions.